So, good morning and good evening, everyone, as the case may be for you. Thanks so much for joining us for our webinar and live demo on improving the security of low-level software components and TEEs. My name is Ashley. I'm the marketing manager at TrustInSoft, who is the leading provider of formal methods-based code analysis tools. I'm joined today by Vic Sharma, who is our US account executive, and he'll be giving you some background on TrustInSoft and how we can help solve challenges in cybersecurity in the semiconductor industry. And I'm also joined today by Jakub Spalikowski, who is our R&D engineer, who will be going through the live demo of TrustInSoft later on in this webinar. So without further ado, Vic, I will go ahead and turn it over to you.
Thank you, Ashley. Semiconductors are at the core of many things we see around us, from game consoles, mobile devices, and smart meters to automotives to aircrafts and equipments used in industrial settings and mission-critical domains such as space and defense. How critical semiconductors are is evident from the recent shortage that has brought the automotive industry to a standstill. It shows how much impact they can have on an entire vertical. Having said that, with the proliferation of consumer electronic devices, IoT equipments in home and industrial settings, and automotives, due to mass adoption, semiconductors continue to see a growth with well over 1 trillion of them sold worldwide annually. While this is an impressive number, it also brings with it some very serious challenges when it comes to the security of millions or rather billions of devices these semiconductors are a part of. Vulnerabilities in low-level software components in the chipsets at the system level can expose these devices to security threats that can have very serious consequences. Here is some information to substantiate that. Over the last 5 years alone, firmware-related vulnerabilities have gone up by over 573%. Over 80% of the enterprises have seen at least one firmware attack in the past 2 years. 4 in 10 companies have been breached through a mobile device. There are very well-known incidents where software at the chip level, including trusted execution environment issues, have exposed millions of mobile devices to security threats. And we all know about cyber attacks on critical infrastructure that are on the rise. Now, the common denominator in all this are the vulnerabilities in the low-level software components that are exploited. These are components such as device drivers, kernels, real-time operating system, and TEEs. Now, what does that mean? This means that preventing device-level attacks that are targeting these low-level software components is extremely critical and is at the forefront of cybersecurity. While traditional methods and tools are used for finding potential issues, they cannot prove complete absence of bugs. And this is what we deliver. TrustInSoft Analyzer is an advanced C and C++ source code analyzer that delivers a mathematical assurance by leveraging advanced static and dynamic analysis techniques combined with formal methods to ensure that this low-level code is secure, reliable, and of the highest quality. There are no guesses or list of potential issues. What you get is a mathematical guarantee by proving absence of vulnerabilities. So one can be rest assured that the firmware code is secure. Now, at the core of what we call sound code analysis is this ability to detect all undefined behaviors. Undefined behaviors, as explained precisely in the C and C++ standards, can be very complex, and if not detected early on, can lead to serious consequences such as unpredictable results or software crashes, which in turn can lead to even bigger problems. So by guaranteeing absence of errors, such as the ones listed here, a buffer overflow, an integer overflow, a divide by zero error, for example, early on in the software development lifecycle, you can address and eliminate potential issues that might arise during runtime. And by mathematically proving program correctness, you can ensure that the code performs the way it is supposed to. So what is the secret behind this? Simply put, the secret is the tool's ability to perform, thanks to formal methods, an equivalent of large number of tests in a short span of time to assess all the possible behaviors of the code that is being analyzed. And by doing that, be able to prove absence of vulnerabilities. So here are a few distinct points that highlight why traditional methods and techniques may not be sufficient when it comes to security of low-level code. Traditional analyzers generally are unsound, that is, they are unable to report all potential problems. TrustInSoft Analyzer performs sound code analysis by ensuring that if a bug exists in the code, the tool will not sit quiet and indeed raise an alarm. Now, traditional approaches perform, for the most part, a syntactic analysis, merely searching for patterns or suspicious code constructs to deliver a list of potential bugs that may or may not be real, and large number of false positives. TrustInSoft Analyzer applies formal methods and performs a deep semantic analysis of the code, analyzing its behavior and checking execution for all possible input values to identify issues and guarantee absence of all undefined behavior. And this results in this low-level code that is secure and of very high quality. So what are some of the examples of this low-level code? We'll talk about 3 different use cases and how we're able to prove the security of this low-level software. The first one is a unique, one of its kind resulting on the ARM Embed TLS stack, which is at the core of the ARM Embed environment. Here, the analysis performed using TrustInSoft Analyzer demonstrated how the stack in a described configuration is immune to vulnerabilities such as buffer overflow. Now, this was a very unique result. NIST, which is the National Institute of Standards and Technology, in its report to the White House, actually mentioned the technology and the fact that we performed a mathematical assessment of absence of buffer overflow on the ARM Embed TLS. The second example was an assessment performed on a device driver. In this case, a driver for a digital output motion sensor from ST Microelectronics, primarily used in automotive applications. Here again, the driver code was analyzed using TrustInSoft Analyzer, and within the perimeter of the defined tests, through exhaustive analysis, the tool was able to mathematically guarantee that for any given input and execution path, there was no undefined behavior in the driver. And the key takeaway here is that it was performed in a pretty short period of time, in less than 1.5 hours, where the analyzer was able to identify an issue, which was buffer overflow. And when it was corrected, we redid the analysis, and the analyzer confirmed that for all existing tests, the driver had no undefined behavior. This third example is a Linux kernel driver for the Goodix capacitive touch chip, which is widely used in mobile phone devices. Here, a formal analysis was performed on the kernel driver using the analyzer, and within the perimeter of the analysis, the tool was able to assess that the driver is secure from a large number of vulnerabilities that could compromise the complete OS. Now, this was indeed an interesting use case for a chip that is widely used in mobile devices and could be compromised if a hacker could simulate a screen touch with multiple fingers or inputs. In that situation, the question was, is the kernel driver robust enough to sustain such an attack? And through an exhaustive analysis using TrustInSoft Analyzer, we were able to assess the immunity of the kernel driver to vulnerabilities within the perimeter of the analysis. And finally, security of trusted execution environment. TEEs, as you all know, are highly secure, but there have been incidents where vulnerabilities within the TEEs themselves have exposed the chipsets and devices they are a part of to security breaches. This is very critical, not just for the semiconductor manufacturer, but also domains that are heavily dependent on it, such as telecom, mobile, consumer devices, and automotive. Here, TrustInSoft Analyzer delivers TEE security by detecting critical firmware vulnerabilities early in the development cycle and providing mathematical guarantee on absence of undefined behavior, essentially covering various subcomponents within TEEs such as kernel, secure, monitor, bootloader, trusted applications to find critical issues, and ensuring that there are no inconsistencies between the expected requirements of the TEE firmware and its implementation. Now, we talked about the technology, but the real differentiator is our unique methodology that incrementally and progressively helps you achieve a high firmware quality. That is our three-phase approach. The first stage is what we call as an interpreter mode or level 1. At this level, we simply replay the existing tests. The analyzer exhaustively detects all undefined behavior. It'll help you find bugs that are very subtle, which otherwise may not be found or you may have missed. In other words, it helps you get the most out of your existing tests. Every bug identified is a real bug. So there's zero false positives and zero false negatives. What you see is real, and you get a mathematical guarantee that all undefined behaviors are detected for your existing tests. Moving on to level 2, which is the analyzer mode, you can progressively increase the number of tests that you can do to reach an exhaustive coverage by generalizing the inputs, which is what you'll shortly see in the demo. You can conduct an equivalent of a very large number of tests to go even further and mathematically guarantee that your code does not have any undefined behavior for all the inputs. So you have still zero false negatives, and you can achieve up to 100% coverage on critical tests. And finally, you can do a functional proof, proving that a piece of low-level C and C++ code is doing exactly what it is supposed to do. It takes a little more time, but through formal proofs, you can see if the software specifications are indeed enforced on the code or not. So how we empower the developers and testers? Number one, by enabling them to exhaustively find and fix all undefined behaviors, including the most subtle ones that they may otherwise miss, ensuring absence of uh, 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 crashes and achieving deterministic behavior of your C and C++ code. Number two, by boosting the software coverage by performing equivalent of a large number of tests with one generalized input, so you can progressively reach a high code quality. And finally, get a mathematical guarantee on absence of undefined behavior, thus ensuring the security of your low-level code. Very quickly, how it is deployed. TrustInSoft Analyzer can be installed on a dedicated server, either on premise or in the cloud. Um, it can be accessed through the web browser and a command line interface, and it can be integrated seamlessly into your existing DevOps and continuous integration processes. So, how we help our customers address these primary business drivers and the value TrustInSoft delivers to address these drivers. Number one, by improving operational efficiency, by reducing the software test coverage costs, by optimizing the bugs identification remediation, essentially focusing on what's real and increasing your software coverage. Number two, by generating revenue opportunity by positioning security and safety, of course, as a feature to gain market share, to get to the right certification level and secure time to market sensitive opportunities. And finally, by controlling the financial risk if and when an issue occurs in the field and potentially avoiding any impact on the brand and image. Now, I will transition over to my colleague who will show a demonstration on one of the examples that I talked about earlier, the Goodix Linux kernel driver. Thank you.
Okay, thank you, Vic. So I'm taking over now. My name is Jakub, and I'm an engineer working in TrustInSoft. So I will show you I will show you a little bit of a demo on the use case that Vic was talking about before, the Goodix driver case. Okay, so what is Goodix GT915? It's a 5-point capacitive touch chip designed for 4.5 to 6-inch mobile phones. It's actually used, or it was used in products from several known companies like Huawei, Lenovo, ZTE, and some others. Here you have an example of a phone where this photo of the chip actually comes from. So it's inside. So what did we actually analyze here? Well, the driver's code was taken from this particular repository, and you have the commit number for reference. If you're interested in that. The official datasheet was used to model the hardware behavior of this device. Unfortunately, or maybe fortunately for some, it's in Chinese, but well, it was enough. So I will not discuss here the way that the analysis was prepared, because enter into this level of detail, well, it would take too much time in this short webinar. But there is a report explaining all the details about that. So if you're interested, we can share the report with you. Okay, so what we did here are two separate analyses with two separate parameters of analysis, which let's say correspond to two ways how we can access the driver. The first one is, let's say, the more natural scenario where we suppose that the attacker has access to the device. So this is like in the example that Vic gave you before. If an attacker can simulate touching the touch screen with 255 fingers, does it cause any problems or not? And in this case, in case of this perimeter, we have actually proven that the driver is completely immune to a whole set of security weaknesses. So this is a very good result. And I'd say this is a natural way of seeing that. But just for fun, we have checked if in other circumstances there are no problems present. So this is more like an artificial scenario where we can imagine an attacker who has a direct access to the proc file for this device. So maybe this kind of situation is actually impossible in practice or difficult. Maybe you need root privileges for this case, but we have checked this case, and actually, if that's the case, if the attacker can write anything he wants to the proc file for this device, there are some vulnerabilities present in the code. There are some undefined behaviors. So let's start with that. Let us see what kind of bugs we have found in this case. So this is the GUI of TrustInSoft Analyzer, and the analyzer is showing something fishy going on here. So a little disclaimer, there is quite a lot to take in here. This is not some kind of a toy snippet of code. This is real code of a Linux driver. So it's pretty complex, and well, the analyzer shows a lot of data. So let's see what's going on here. First, on the right, you can see here on this right pane, this is the original source code of the driver. As you can see, this is the file Goodix tool. The line memcopy is here marked, and this is in the function Goodix tool read. So this is the actual code of the driver. Here in the middle, that's where the most important things are going on. This is the interactive version of this source code on the right. So this is equivalent to the source code of the on the right, but you can explore it, and there is some information added to it that is not in the original source code. Like, for example, here I can see this, all the code marked in red is dead code. So this is the code that was not reached. It's unreachable in this perimeter of analysis here. And this is how the analyzer tells me that there is a problem in the code. I will just come back to here to this place in a few seconds. I will just tell you about the rest of the interface before to just finish this little overview. So here on the left, you have a lot of details about what's going on. The most important part here is this line. One potential undefined behavior has been found. This says that, yes, the code is not sure to be free of bugs, and there is actually one bug that that was found by the analyzer. Here on the bottom, we will see the values of things, of variables, basically from the code. So let's get back here and see what's going on in this line of code and what this assertion about. So TrustInSoft Analyzer is not like most other traditional static analysis tools, because it's not trying to find bugs, it's actually trying to prove that there are no more bugs in your code. So instead of saying, I found a bug, it will say, oh, there is some property of a code that I cannot prove to be true. In this case, basically, it means that the read of this address at this offsets is valid. He says, I cannot prove it, so it basically means, yes, there is an invalid read here, most probably. So now I can use the analyzer to understand what's going on here. I can, for example, click here on the comment head address, which is the second argument of our memcopy function. And I can see what are the values inside this field of the structure and what is actually this structure. So I can see that this is a global variable or a static variable with it's an array of type U8 of two fields, and both cells of this array have this special top value. This value means that they can contain any possible value of the type that is given here. What is this type exactly? I can click on that and see that it's unsigned char. So this means that here I have two cells of an array, and both of them can have any value from 0 to 255. Now, if I check the other thing here, the length that is given to the memcopy function, I will see something quite similar. So it's also type U8, and it's a top value here. So it's also from 0 to 255. And this is already, so this looks pretty dangerous, because we can see that we are reading out of bounds here. So if this value is 0 or 1, everything is going to be fine, because we are in the bounds of this table, of this array. Otherwise, we're going out of bounds. So this assertion, this problem signaled here, looks to be a real problem going on, which looks pretty dangerous. Just for comparison, let's see how a precise value looks like here. So if I click on data_len and this particular line where it's an assignment is going on, I can see that this is a U16 value, and before this assignment, its value is 0. After, the value is 256. So this is this is a very precise value, just one possibility here. And here, what's interesting, I can see that I'm able to use the TrustInSoft Analyzer like kind of an advanced debugger. I can go backwards and forwards in the execution of the program and see exactly at which points what's going on. So I have full semantic understanding of what is going on in the program. Okay, let's go back to our bug here. What I can do now to understand what's going on is to find out where are these values coming from. So this address len. And I'm using this feature called ShowDevs. And now on the left here, I have this little list of ShowDev statements, which tell me where in the whole code that is analyzed, I assign, I change the value of this field in a way that affects it at this point. So the only one that of this assignments that is direct is here. And this is actually a memcopy performed in copy from user function. So this looks, again, quite dangerous. So I can see that this length here is actually directly taken from user space, probably to kernel space, which is probably not a very good idea. So here, what I can see is that the length is 20. where I'm copying from is this variable, the address of variable ThysBuff user order, and what I'm copying to is actually the whole structure, comment head. If I look inside here, I have actually a whole information about what is going on in the structure at this point. So what is there before the copy, and I can see that address length at the beginning is equal to 2. So if it stayed equal to, we wouldn't have the undefined behavior. But after the copy, well, it became, as you can see, top here. So its value is abstract. It can have any value from 0 to 255. Okay, and now let's see what can I do more. I will go up in the call stack. I will go to the color of this function, and again to the color. Now I'm in function Goodix tool right, and when I go one step up, I'm getting to this this place here, this function, thisProcWrite. So this is function that I have written, which is actually implementing this scenario, this perimeter of, no, sorry, not this perimeter. It's implementing the fact that the attacker can write anything to the proc file. So here what I'm doing, I'm preparing this buffer, which is called ThysBuff user order. So this is the variable that we, the buffer that we used to copy information to the length variable that we have seen before. So I start by making it completely abstract. You can see here that it's before this this line, it's all uninitialized, and after this line, it can have any possible value. This is done using this special function thisMakeUnknown, which is rendering parts of memory abstract. And then I proceed to set some particular fields of the structure to particular values. So here, what is interesting is that how to understand it. So this is the buffer that I get that I'm passing then to this function here, and this is so this is prepared by us, and all these fields here where I have this value top are abstract, and all the other fields have some precise values. So when I say abstract, it doesn't mean that it's some kind of random value in this there, or that we something like that. It's really as if I was trying all the possibilities at the same time. So if I was analyzing all the combinations of values in all these fields that are possible. And this is quite a huge number of combinations. So even here you can see that there is this, at the end, there is this buffer, which is around 4,000 bytes. These are chars. So this this thing corresponds to 256 to the power of 4,000 combinations. So it's as if I was doing this number of tests, actually. It's equivalent, and I'm able to take this object, which is abstract, and give it as an argument to a function. So use it as if it was a concrete object, and analyze the code this way. Okay, so let's see how does it look in the source file here. So this is what you can see as the entry point for the analysis here, the main function. What I'm doing here is I initialize the driver, I probe the hardware, and then I simulate this one of the scenarios that I was talking about. So here, the first one is commented out. I'm just trying to write and read from the proc file. This is the one we're doing, and this is the function that we have just seen, this ThysProcWrite. So you can see here that that's exactly what I done before for the abstract values. And here I have actually found a concrete value. Well, I did it before that satisfies that triggers this UB. So now I will uncomment this code and I will relaunch the analysis in the background so we can see how it looks like. So we can see that this actually there is a case where this this behavior is triggered. Sorry, yeah. We're here. Okay, let's go back to our undefined behavior. Yeah, so we can go here and see that that actually there is this line here now, address length equal 10. And when I go to my undefined behavior, I can see that command head address len has value 10 now. So this is what I put there. So we can see that this indeed it's coming directly from data given by the user, written by user to the proc file. Okay, so just to finish it on a, let's say, positive note, let's see what happens when I try out this more natural, normal scenario when I when I'm simulating the access from the touch screen side. So here the idea is that I have an infinite loop where I'm calling all the interrupt handlers of the registered by the driver in well, in loop infinitely. So the cool thing is that TrustInSoft Analyzer is using mathematics to understand all that. So it can actually analyze infinite loops and say, okay, maybe it doesn't terminate, but I am sure that no matter how long this will run, there are no bugs which will happen. And that's exactly what's going on here. So this is, let's say, a boring case, because the most important thing to see here is that now I have the information, no undefined behavior found in the program. And this is pretty cool, because this is an actual guarantee that in this parameter of analysis, there are no undefined behaviors present in the code. And I can just for fun, I can just descend here to see what's going on in this interrupt. So I'm going quickly now. There is no, and I will arrive at some point at the function Goodix TS work func, which is handling the interruption. And I can see that here actually there is this variable finger which can have any possible value. So it's also U8, so it can actually, we are actually checking if 255 fingers at the same time are fine or not. Okay, so that's it. That's it for now. What I like to conclude all this, I would just say that this is the kind of results that TrustInSoft can give you for this kind of component. So it can help you to find very subtle vulnerabilities in different contexts, or it can prove the absence of undefined behavior in a certain context with a mathematical guarantee. That's it.
Okay, thanks so much, Jacob, for doing that demo on the Goodix driver for us. We have just a couple of minutes left here, and I would like to give you and Vic the opportunity to answer the questions that we have. So as a reminder, if anyone has questions about the demo or the presentation, feel free to go ahead and ask that in the chat. So I see we have a first question here. So let me just display this question. So this is a question from Nathan. Does the analyzer work on just C and C++, or does it analyze the assembly code?
I can maybe just take a stab at it, and if you want to add anything, Jacob. So the analyzer does work only on C and C++ code and not the assembly code.
Yes, this is correct. The analyzer works on C and C++ code using the C or C++ standards to actually understand the semantics of the code. And there is Java as the next language in the roadmap. When we encounter assembly inlined in C or C++ programs, we can handle it in different ways. If we are sure to know what it does, we can just stab it with some C code. Otherwise, we assume nothing about what happens in there, and the power of like formal methods and mathematic analysis can let us see what's going on with the code if we don't know anything about what happens in this part. Yeah, that's it.
Okay, great. And I have another question from Mattia, which is, what do we mean by semantic analysis?
All right, well, I'll take a stab on this as well. To start with, so what we mean by semantic analysis is really, rather than focusing on the syntax, or for lack of better words, the grammar of the underlying language of C or C++, we focus on the behavior of the code, essentially, which means for a given set of inputs, or for a generalized input, as Jacob explained earlier, the tool checks for all the possible executions of the program that's being analyzed. So you can assess the behavior, and more than that, assess if it will deviate from what it's supposed to do, if it will show an undefined behavior. And that's what we mean by the semantic of the analysis, basically assessing the behavior. You want to add anything to it, Jake?
Yeah, I think you said basically everything that's important. So what I can add is that, as I mentioned just before, the semantics here are defined by the C or C++ standard, and thanks to that, we can understand exactly what is going in the code, not have just superficial understanding, but understand what is really going on during the execution of the program.
Okay, great, thank you. And we have another question here, also from Mattia. In the context of TEEs, how do you address buffer overflow, side channel attacks, or concurrency issues? Which was mentioned, I think, earlier in the presentation.
Sure. Well, to start with, as I explained earlier, the TEEs by itself are highly secure, but they can be compromised. The subcomponents within TEEs can be compromised. So, for example, an issue like a buffer overflow in, let's say, a trusted application, or the TEE kernel can be exploited to gain access to the Linux kernel itself, and can compromise the device it is running on. So essentially, within that context, what we do is prove absence of issues such as a buffer overflow. If I could say, the goal is to be able to see those subtle issues that otherwise could be missed in this core part of the firmware, the subcomponents of the TEs. So that, I think, is the important thing, is be able to identify these subtle bugs that one can miss. And second, to be able to prove that the firmware is indeed in line with its specification, or rather implementation of the firmware is in line with the specifications, and it doesn't exhibit any undefined behavior. And of course, the final goal in the context of all the issues that are in this question is to be able to show that the TEE subcomponents and the underlying code is reliable and secure and deterministic, basically. Anything you want to add to that, Jacob?
I can just maybe say that there are three wildly different kinds of problems mentioned here. So address buffer overflow is the kind of thing that we have seen in the demo here, because this is an undefined behavior, typical one. But so this is the thing that the analyzer is doing on the level 1 and level 2, which Vic mentioned before in the presentation. But we also have plugins to check for other problems, like, for example, side channel attacks, so like timing attacks. We have a plugin, TrustInSoft Analyzer has a plugin for checking that, and also for some concurrency issues. So we can handle all this, all the three of these problems.
Okay, great. And I have one last question here as well from Nathan. To clarify, by provable, you mean that all inputs paths are tested, correct?
Do you want to take that, Jacob?
Yes. So I think the short answer, provable. The short answer would be that yes, this is what we mean. So the concept of the analysis perimeter comes it's important here, as I have showed before, it is important to the notion of all inputs or paths. So I decide which kind of inputs or paths I want to test correct. And I can, for example, as in this case, test all the possible things that are written on the proc file. But so the most part of the message written on the proc file, the data written on the proc file, is any possible values. But I have still put some data there, so I didn't do all of them totally. So there is always kind of a choice of what kind of coverage I want to do, and usually we are enlarging the coverage. So we are usually starting with, for example, just one code path based on a single unit test or a single let's say entry point, and then we generalize the values of variables or inputs to see what's going on. If we don't find any problems on one path, we generalize stuff and values everywhere in order to attain the coverage that we want. Hopefully, complete coverage, 100%. That's it, I think.
Okay, great. So I think that's all of the questions that we have for now. However, if you have any additional questions, don't hesitate to reach out to us after the webinar. You'll be receiving the slides and the replay this week, so keep an eye out for that email. And we hope that you enjoyed the webinar and it was informative for you. And as always, feel free to reach out if you would like to have some more information about TrustInSoft Analyzer. So I think we can go ahead and close the webinar. Thanks, guys, and see you next time.
Thank you, everyone.